Hey everyone, welcome back to our networking series. Today we are diving into one of the most important concepts in networking, the OSI model. A bit traveling from one computer to another can be hard to understand. In 1984, the OSI model was created to explain how computers communicate over a network. The OSI model divides network communication into 7 layers. These layers work together to form a message. The message is created and it moves through each layer, but it is not sent to the network until it reaches the physical layer. This model helps IT, computer science, and cybersecurity professionals to understand how data travels from one computer to another. Also, it enables understanding of network protocols, security, and flaws in system. It covers all aspects of networking, from physical devices to user interfaces. It provides a structured approach to understand how data is transmitted and received across a network. So here is what we will cover in today's video. Let's start by understanding what OSI model is. Next, we will discuss why it is important. Then we will explore how data moves through the layers of OSI model. Moving further, we have a detailed breakdown of 7 layers from physical layer to application layer. After that, we will compare the OSI model with TCP/IP model. Finally, we will look after the benefits and advantages of using OSI model. Let's get started. What is OSI model? The OSI model is a framework that explains how computer networks communicate. It divides the networking process into 7 distinct layers. Each layer has its own specific functions. This structured approach facilitates interoperability between different systems and helps in design and troubleshooting of network communications. Now let's talk about the framework type. Framework type means the kind of system or a model. The OSI model serves as a conceptual framework that helps professionals think about networking processes and understand how different components interact. It acts as a reference architecture for designing network protocols, ensuring that various systems can work together effectively. The model provides a standardized approach to networking, which makes easier for different systems to communicate with each other. Now let's move on to structure of OSI model. Here structure refers to how something is organized. The OSI model is divided into 7 layers, each with its own specific functions. It follows a hierarchical design, meaning it starts from the bottom and works its way up. In OSI model, each layer is modular, meaning you can modify one layer without impacting the others. Now let's discuss the origin of OSI model. It was created in late 1970s and early 1980s. It was created to solve the problem of different computer networks not being able to communicate with each other. Early networks from different companies were incompatible, making it hard for them to communicate. For that, ISO and CCIT worked on a solution. Therefore, the OSI model was developed as a standard framework and was officially published in 1984 to guide how networks communicate. And that was a quick historical note. Now let's move on and understand why it is important. The OSI model is important for several reasons. First, standardization. It is a process of establishing common standards or protocols that everyone follows. These standards make sure that products or systems from different manufacturers are designed to follow the same guidelines. For example, standards like Ethernet, IEEE 802.3 or HTTP define how devices communicate on networks. So standardization is about setting rules. Next, interoperability. It is a result of implementing standardization well. It allows various systems to exchange data and work together smoothly. Interoperability is ability of different systems, devices or applications to work together and communicate, even if they are from different manufacturers or use different technologies. For example, devices from different manufacturers like Cisco and Juniper routers can communicate on same network because they both follow standardized protocols like IP. Next, it is an educational tool. It is a conceptual framework used to teach how networks operate and how different layers interact. It breaks down complex processes into layers, which makes network communication more understandable. For example, the OSI model is often used in courses to explain how data travels from one device to another. Next, layer independence. Each OSI layer functions separately with distinct responsibilities without interfering with other layers. And thus it ensures modularity where changes in one layer does not affect others. For example, the transport layer can manage flow control without worrying about physical connections in data link layer. Next up, service relationships. Each layer serves the one above it by providing specific functions and passes information up or down. Thus, it enables clear communication between layers, ensuring that they rely on each other in a structured way. For example, the network layer provides routing services to transport layer, which handles end-to-end communication. And next, we have data flow. Data is encapsulated with layer-specific information as it travels down the layers and decapsulated as it moves up. Therefore, it ensures accurate data transmission by adding headers or trailers specific to each layer's functions. For example, the application layer sends data and each lower layer adds its own information before sending it. Now let's understand how OSI works. The OSI model consists of two major components, which are abstract model of networking, also known as basic reference model or 7-layer model. This component provides a structured framework that divides the networking process into 7 distinct layers. Next, a set of specific protocols. They operate on each layer. These protocols define the rules and standards for communication within and between layers, which ensures that devices from different manufacturers can work together effectively. Now let's understand how OSI works with a real-world example. When we send an email to someone, what does really happen? This table illustrates the OSI model layers and their corresponding functions, protocols, and processes involved in sending and receiving an email. What happens when client sends an email to server? We will see layer by layer. Sending an email begins at application layer. First, the user composes an email using an application like Outlook or Gmail. At this layer, the email is prepared to be sent using a protocol called SMTP. This protocol sends commands to email server. Next, in presentation layer, the email is converted from computer's format to network-friendly format, and this is done using compression or encryption. In session layer, the connection is established between client and server. This is done by SSL TLS protocol. Here the connection is established. This layer manages communication and ensures email is transmitted properly. In transport layer, the email is broken into smaller segments. These segments are labeled with sequence numbers so that they can be reassembled correctly on the recipient end. In network layer, the segments are packed into data packets. The source and destination IP addresses are assigned, and these packets are now ready to be routed across the internet. In data link layer, the packets are converted into frames which are ready to be transmitted over the local network. The physical address or MAC address is added for local delivery. Finally, in physical layer, the frames are converted into electrical or optical signals, and it is transmitted as bitstream over the physical medium through Ethernet cable or Wi-Fi. Now the intermediary part, that is the router processing. As the email moves through different networks, routers process it by updating the data link layer information. That is, routers remove and replace network address information to adapt different networks. Therefore, router adjusts the details of each network and forward the email based on its IP address and ensuring it gets closer to its destination. Now the reverse process, that is at server side. At server side physical layer, the bit stream is received and converted into frames. These frames are passed to data link layer. Next, in data link layer, the frames are reassembled into packets and sent to network layer. In network layer, IP addresses are verified and packets are reassembled into segments and passed to transport layer. In transport layer, the segments are reordered based on the sequence number and reassembled into original email data. In session layer, the session is terminated once the email data is fully received, and then it passes the email data up for further processing. In presentation layer, the data is decrypted and decompressed if necessary, and then passed to application layer. Finally, in application layer, the email server delivers the email to the recipient inbox, making it available through POP3 or IMAP. And that's how an email travels across the OSI layer from sender to recipient. The table provided is about how email is being transmitted over wired network, such as through Ethernet. The data travels over physical cables, and protocols like Ethernet for data link layer are typically for wired network communication. If the network were wireless, such as using Wi-Fi, the same OSI layer structure is applied. But some protocols at physical and data link layers would change. For example, instead of Ethernet, you would use IEEE 802.11 at data link layer, and in physical layer, the transmission is over radio frequencies. Now look at the table. In wireless network at data link layer, the IEEE 802.11 protocol is used instead of Ethernet. This protocol handles communication over wireless LAN and assigns MAC addresses for wireless devices. In physical layer, instead of using physical cables like Ethernet, the physical layer transmits data as radio waves. Therefore, in wireless transmission, devices communicate each other without being physically connected. And thus the data link layer uses Wi-Fi to frame and transmit data, while the physical layer sends these frames as radio signals to wireless receivers. On the receiver side, the process works in reverse. Here we convert the radio waves back into data. Now let's understand a more zoomed view of OSI layers. OSI layer can be categorized into two groups based on their responsibilities, which are host group and network group. Host group are upper layers. The upper layers deals with end-to-end communication and are responsible for data processing and interpretation that happens on sending and receiving devices. They are also referred to as software layers or upper layers. The host group includes application layer, presentation layer, session layer, and transport layer. Application layer directly interacts with user applications and provide network services like file transfer, email, and web browsing. Presentation layer is responsible for data formatting, encryption, and compression. It ensures the data sent by the application is readable by the recipient. The session layer establishes, manages, and terminates communication sessions between devices. The transport layer ensures reliable data transfer between hosts using error detection, data segmentation, and reassembly. Next up, the network group, which are lower layers. These layers deals with actual transmission of data across the network. They ensure that data can travel from one host to another and handle data transmission over different types of networks. The network group includes network layer, data link layer, and physical layer. Network layer is responsible for routing data between devices across multiple networks. It assigns IP addresses and determines the best path for data to travel. Data link layer handles communication between devices on same local network. It packages data into frames and provides error detection and correction at this level. The physical layer manages the physical connection between devices and transmits the raw bit stream over the medium. The host group is responsible for processing the data on devices and ensures it is properly prepared and received. The network group handles transmission of data across the network infrastructure, which ensures that it reaches its destination. Now let's understand each layer in detail. First, physical layer. It transmits raw data over physical mediums. It deals with physical connection between devices and transmits raw bit streams, that is zeros and ones, over physical mediums. This layer defines how the network is physically laid out, whether in star, ring, or mesh configurations. It also specifies data transmission standards like signal voltages, timing, and data rates for communication. It converts data bits into electrical, optical, or radio signals and vice versa. In the physical layer, several hardware elements and protocols are involved. Cables like Cat5e, Cat6, fiber optic, and coaxial cables are common transmission medium. Jacks such as RJ45 connectors and patch panels organize and connect these cables. Hubs connect multiple devices, while network interface card allow devices to connect to the network. IEEE 802.3 is a protocol widely used in LAN. It defines how data is transmitted over cables. USB is a protocol and hardware used to connect peripherals like keyboard, mouse, storage devices, and also allow data transfer between them. Bluetooth is a wireless standard for short-range communication between devices. RS-232 is a standard protocol for serial communication. It is often used with modems and printers. The USB, Bluetooth, and Ethernet are examples of standards that define how devices connect and communicate at physical level. They specify how data is transmitted over cables or wirelessly. Now let's understand the responsibilities of physical layer. First, bit synchronization. The physical layer ensures that both sender and receiver are in sync with respect to timing, so they can accurately transmit and receive data signals. Next, bitrate control is another key function of physical layer. It defines how fast data is transmitted over a communication channel, and typically it is measured in bits per second. The data transmission rate depends on physical medium like copper cables, fiber optics, wireless signals. There is different types of physical media have different capacities for transmitting data. For example, fiber optic cables can support much higher bit rates than copper cables, and wireless signals have limited capacity compared to wired connections. Similarly, the quality of a signal being transmitted affects the bit rate. For example, a strong, clear signal can support higher bit rates, whereas a weak or noisy signal may require a low bit rate to maintain accuracy. And one more factor that affects the bit rate is distance. When longer the data travels, the signal gets weaker, which will slow down the data speed. Next, the physical layer defines the transmission mode. Transmission mode means how data flows between connected devices. There are three main types: simplex, half duplex, and full duplex. In simplex mode, data flows in only one direction from transmitter to receiver. For example, TV broadcast. In TV broadcast, the TV station, that is transmitter, sends video and audio signals to the TV set, which is the receiver, in only one direction. The TV set receives the signal and displays the program, but it does not send any data back to the TV station. And this is a one-way communication. In half duplex, data flows in both directions but not simultaneously. Example, a walkie-talkie. Here one person talks and other listens. Then the roles are reversed. In full duplex mode, data flows in both directions simultaneously. Example, a phone call where both parties can talk and listen at the same time. The physical layer also defines the physical topology of a network. It tells how devices and nodes are physically arranged or connected. Common topologies include bus topology, star topology, and mesh topology. In bus topology, all devices are connected to a single communication line. Here data travels along this shared line. In star topology, all devices are connected to a central hub or switch, which makes easy to manage but dependent on central device. In mesh topology, every device connects to every other device, providing high redundancy and reliability. The physical layer also defines how data is encoded and transmitted. Data is sent using different methods such as electrical signals through cables like Ethernet, radio waves for wireless connections like Wi-Fi or Bluetooth, and light pulses through fiber optic cables. There are many encoding schemes in which data is encoded like Manchester encoding and differential Manchester encoding scheme, etc. Look at the image. You can see how data is encoded into Manchester encoding form according to clock pulse. On receiver side, the physical layer accepts the electrical signal that is received and decodes that signal and makes two stream of bits, and it sends it to upper layer, that is data link layer. And next layer is data link layer. This layer ensures that data transferred over the physical layer is reliable and free from errors. It takes the raw bits from physical layer and packages them into frames. Frames are structured data units. These frames helps in organizing data, detect errors, and ensures that communication between devices is more reliable. Here are the components of frame: frame header, payload field, trailer, and flag. Frame header includes the frame's source and destination addresses. Payload field includes the message that need to be delivered. Trailer contains the error detection and correction bits. Flag points to starting and ending of a frame. The data link layer is divided into two sublayers, which are logical link control and media access control. Logical link control acts as an interface between data link layer and network layer. The logical link control is positioned above medium access control sublayer. Its responsibilities include multiplexing, flow control, and error checking. Multiplexing means it enables multiple network protocols such as IP and IPX to operate simultaneously over the same physical medium. Multiplexing maximizes the use of network resources by preventing interference between different types of data, which leads to improved overall network performance. Therefore, multiplexing in LLC sublayer enhances the efficiency and effectiveness of network communication. Next, flow control. It is about managing the data transmission rate to prevent overflow at the receiver's end. Flow control techniques include stop and wait, sliding window. Stop and wait method is a basic reliable method. Here the sender waits for an acknowledgement before sending the next frame. Sliding window is more efficient technique which allows sending multiple frames before requiring acknowledgement. Therefore, flow control prevents data loss. That is, by controlling the flow, it reduces the chance of data loss due to buffer overflow at receiver side. Also, it enhances reliability, which ensures that data is transmitted reliably and efficiently. Thereby, it maintains the integrity of communication. And next, error checking. It finds error in data transmission and prepares for retransmission if packets fail. Thereby, it ensures data integrity. Next, the MAC layer. This layer controls how devices access the network medium and how data is transmitted. MAC layer specifically decides when a device can send the data and also ensures proper transmission of data between devices. MAC layer operates directly above the physical layer. And these are the functions of MAC layer. First, frame delimitation. The MAC layer defines the start and end of data frames, which ensures that data is properly structured for transmission. This includes adding necessary headers and trailers. Next, addressing. Each device on a network is assigned a unique MAC address. It is 48 bits long. The MAC layer uses these addresses to identify the source and destination of frames. Next, error detection. The MAC layer implements error detection mechanisms such as frame check sequence and CRC to ensure data integrity. These mechanisms help to identify any errors that may occur during transmission. Next, fragmentation and reassembly. MAC layer splits larger packets into smaller frames for easy transmission and puts them back together at the destination. Next, access control. The MAC layer manages how multiple devices share the communication medium to prevent collisions. Collision management protocols are used to handle or avoid data collisions in network communication. And here are some common protocols. CS3591 protocol is used in wired networks like Ethernet. It detects collisions in wired networks and retransmits data if a collision occurs. CS3591 protocol is used in wireless networks like Wi-Fi, which avoids collision in wireless network by signaling before sending data. Next, token passing. Token passing is a network protocol which manages access to shared medium. In this method, a special data packet called a token is generated and circulated among the devices in the network. Only the device which holds the token can send the data on the network. If a device wants to transmit a data, it must wait until it receives the token. Once a device receives the token, it can send its data. After completing the transmission, the device releases the token back onto the network. The token is passed in a set order, so each device gets its turn to send the data. If a token is lost due to malfunction or failure, common recovery mechanisms like token timeout, monitor station, and election protocols regenerate a new token to maintain network functionality. And next functionality is MAC addresses. MAC layer is responsible for handling MAC addresses. MAC address is a unique identifier assigned to each device. It is represented by 6 pairs of hexadecimal numbers. And you can see in the figure, these addresses help the MAC layer to direct the data to correct device. Next, the protocols used in data link layer. Ethernet, it is a widely used protocol for wired network which manages data transmission between devices. Next, link access procedure and network control protocol. These protocols are used for managing data transfer in networks like X25. Next, ARP, address resolution protocol. It translates the IP address to MAC address, which allow devices to communicate on local networks. Next up, SLIP, Serial Line Interface Protocol. It is used for point-to-point connections, mainly for dial-up internet. Next, Wi-Fi. It is used for wireless networks, which allows data transfer over radio waves. Next, SDLC, Synchronous Data Link Control. It is used in mainframe computer networks to control synchronous communication. So these protocols helps to manage data transmission and device communication at data link layer. Now let's move on and understand the data link layer functions. First, framing. Framing is how the data link layer organizes data by adding markers at start and end so that receiver knows exactly where each piece of data begins and ends. Next, physical addressing. The data link layer converts IP address into MAC address and includes sender and receiver's MAC address in each data frame. And this is done using address resolution protocol. Next, error control and flow control. The data link layer detects error like lost or damaged data frames, and it can resend data if needed to make sure it is correct. Next, flow control. To prevent overload, the data link layer controls data flow by making the sender wait for a response before sending more data. Next, access control. When several devices share a network, the MAC sublayer manages which device can send data so that it can avoid collision. The next layer is network layer. This layer is responsible for moving packets from source to destination across multiple networks. The network layer finds the best path for data to reach its destination even if it has to pass through other networks. And it uses IP addresses to identify each device, so data knows where to go. The network layer breaks large pieces of data into smaller chunks called packets, so they are easy to send and puts them back together at the destination. In short, network layer makes sure data can travel between different networks smoothly. Here are the key elements involved in network layer. Routers and switches are critical devices in network layer. Each serves distinct roles in managing and directing data traffic. Routers connect different networks and choose the best path for data to travel from one network to another. They work mainly at network layer of OSI model. Next, switches. It works mainly at data link layer of OSI model. It directs data within a single network like LAN. Some layer 3 switches can also perform basic routing. Here are some key features of routers. Routers maintain routing tables that contains information about topology of network and the paths to various IP addresses. Routers use IP addresses to identify devices on different networks and forward data between networks. And it facilitates communication between different networks like LAN, WAN, and Internet. Next, traffic management. Routers can implement quality of service which helps to manage internet traffic. Thereby, it makes sure important things like video calls get priority over less important things like downloads. So this way video calls work better even when the internet is busy. And next feature is network address translation. Routers can modify the source or destination IP addresses of packets. This allows multiple devices on private network to share a single public IP address. Now let's understand the key features of switches. First, packet switching. Switches use MAC addresses to send data only to the correct device in the same network, so that it reduces extra traffic. Switches maintains a MAC address table, from which it learns and remembers the devices connected to their ports, and thus it enables efficient forwarding. Switches can create separate collision domains for each connected device, which enhance network performance and reduce collisions. Next, some switches have routing abilities, which allow them to make routing decisions and handle IP traffic similar to routers. Therefore, both routers and switches are essential for ensuring efficient and effective communication across networks. With routers, we can manage data flow between networks, whereas switches optimize data transfer within a single network. These protocols are responsible for addressing, routing, and managing data traffic on the network. First, IP. There is Internet Protocol. It is a primary protocol for addressing and routing data packets between devices on different networks. This protocol has two main versions, IPv4 and IPv6. IPv4 uses 32-bit address which support about 4 billion unique addresses. IPv6 uses 128-bit addresses which offers nearly unlimited number of addresses for future needs. Next, Internet Control Message Protocol. It is used for error reporting, diagnostics, and network troubleshooting. This protocol enables ping and traceroute commands to work. Ping uses ICMP to send an echo request to another device. It checks if a device is online. It sends a request and waits for a reply. Whereas traceroute uses ICMP, sometimes UDP, to trace the path packets take across networks. It shows the path data takes to reach a device. It sends messages with increasing limits and sees where they stop along the way. In short, ping checks if something is there, and traceroute shows how to get there. Next, Internet Group Management Protocol. It keeps tracks which device want to receive data sent to a group. This protocol is used for multicasting, like streaming videos to many viewers at the same time. It helps in sending data to multiple devices efficiently, so it doesn't have to send separate copies to each one. In short, IGMP helps devices to join groups to receive same data together, which makes it easier and faster. Therefore, these protocols work together to ensure data can travel across different networks reliably and efficiently. Now let's understand the network layer functions. First, packet fragmentation and reassembly. Network layer breaks down larger data packets into smaller pieces, so they can pass through networks with size limits. The sender fragments the packets and the receiver reassembles the pieces to restore the original data. And next up, traffic control. Network layer manages data flow to prevent network congestion and maintain performance. Traffic control technique prevent network congestion, prioritize important traffic, and optimize bandwidth usage. Traffic control technique includes methods like quality of service, traffic shaping, and load balancing to ensure that critical applications like video conferencing or online gaming perform well. Therefore, these functions ensures data can move smoothly and accurately across complex networks. Next layer is transport layer. The transport layer or layer 4 of OSI model is responsible for ensuring reliable communication between devices over a network. It manages data flow control, segmentation, and error correction to facilitate end-to-end communication and maintain the integrity of data as it travels across the network. This layer plays a crucial role in overall functionality of network communication. Now let's understand the key elements of transport layer. Segments are data units used in transport layer. It is created by breaking down larger application data into smaller pieces for efficient transmission. Each segment consists of two main parts, which are headers and data payload. Headers contains control information necessary for data delivery. The key components of header includes source port number, destination port number, sequence number, acknowledgement number, flags, and checksum. Source port number identifies the sending application on the source device. Destination port number identifies the receiving application on the destination device. Sequence number is used by TCP to keep track of order of segments. Acknowledgement number indicates the next expected segment, which ensures reliable delivery in TCP. Control flags like synchronize, acknowledge, and finish manage connection states. Checksum is used for error checking to ensure data integrity. Next, data payload. It contains the actual application data being transmitted. So this structure allows transport layer to manage and track each segment, which supports reliable and ordered data transfer. Now let's discuss two primary protocols used at transport layer. First, TCP, Transmission Control Protocol. TCP establishes a connection between sender and receiver before data transmission begins. This is done through a process called TCP handshake. TCP ensures reliable, ordered, and error-checked delivery. It is suitable for applications which require data integrity like file transfers, web browsing, and email. Next, UDP, User Datagram Protocol. UDP does not establish a connection before sending. Here, each packet or datagram is sent independently, which allows for faster transmission. Therefore, it provides a faster, connectionless data transfer without error checking. It is ideal for real-time applications like streaming and gaming. Now let's understand the transport layer functions. First, service point addressing. Service point addressing means assigning unique port numbers to application on a device. It ensures data is directed to the correct application on the device. So, main purpose of service point application is to allow multiple applications to communicate over the same network connection without interference. So, each application listens on specific port number which act as an endpoint for communication. For example, when a web browser connects to a web server, it typically communicates over port 80 used by HTTP or port 443 used by HTTPS. The port number helps operating system to route incoming data to correct application. And next function is attaching headers. Attaching headers refers to process of adding control information to the data segment being transmitted. This is done by creating a header that contains various necessary fields for proper handling of data. The control information includes source port, destination port, sequence number, acknowledgement number, HLEN, RES, flags, window size, checksum, urgent pointer, options. Source port is port number of an application sending the data. Destination port is port number of an application receiving the data. Sequence number keeps track of data order. Acknowledgement number confirms data received and tells what to expect next. HLEN, it shows the length of the header, so receiver knows where the data starts. RES, reserved. It is a reserved space for future use, usually set to 0. Next, flags. Flags are small indicators that control the connection. SYN, synchronize. It starts a new connection. ACK, acknowledgement. It confirms the data has been received. FIN, finish. It ends an existing connection. PSH, push. It sends data immediately. RST, reset. It ends the connection if there is an error. URG, urgent. It marks data as urgent. Window size controls how much data can be sent before needing an acknowledgement. Checksum checks for data errors during transfer. Urgent pointer. It marks urgent data that should be prioritized. Options are extra settings if needed, like timing or segment size. So these components helps the transport layer to manage data transfer, reliability and order. Next function is flow control. It regulates the speed of data transmission to avoid overloading and ensures smooth and reliable data transfer. Next function is multiplexing. It allows multiple applications on a device to share a single network connection by using different port numbers. We know that transport layer uses the port number to direct incoming and outgoing data to the correct application. For example, HTTP traffic might use port 80 while email traffic uses port 25. Therefore, this allows multiple data streams to be sent simultaneously over a same connection without interfering with each other, and thus it ensures efficient use of resources. Transport layer provides two types of service, which are connection-oriented service and connectionless service. In connection-oriented service, before data transfer begins, a connection is established between sender and receiver using a handshake process. Example, TCP three-way handshake. Data is sent in an orderly manner. The receiver acknowledges each packet, ensuring reliable delivery. Once data transfer is complete, the connection is properly closed. For example, TCP connection termination with FIN flag. This service is reliable. Acknowledgements and retransmissions are used to ensure data integrity. It is slow due to setup and acknowledgement process. Next, connectionless service. Here data is sent without establishing a connection first, and there is no need for acknowledgement from the receiver. The receiver does not confirm receipt, which makes the transfer faster but less reliable. This service is faster because there is no connection setup or acknowledgement. At the same time, it is unreliable because there is no guarantee that data will be received or in correct order. TCP is common connection-oriented protocol and UDP is common connectionless protocol. Next layer is session layer. Session layer is layer 5 of OSI model. It manages and controls the connection between computers. It establishes, manages and terminates session between applications on different devices. It is a logical connection responsible for allowing continuous data exchange between two applications. Apart from that, it also helps in managing authentication, authorization and synchronization. Now let's discuss the key elements of session layer. It includes session. Sessions are connections that are established and maintained over time to support continuous data exchange between applications. And next, the protocols. The session layer includes protocols like NFS, Network File System, PPTP, Point-to-Point Tunneling Protocol, RPC, Remote Procedure Call, NetBIOS, Network Basic Input-Output System. NFS allows users to access and share files over a network as if they were on their local storage. It enables multiple clients to interact with files stored on a central server. Therefore, it facilitates file sharing in network environments. Next, PPTP. It is used for creating virtual private networks. It provides secure remote access to networks over the internet. Next, RPC. It allows programs to execute functions on a remote server. It supports distributed applications by enabling communication between different systems. And next, NetBIOS. It enables applications to communicate over a local network. It is commonly used in Windows environment for file and printer sharing. Now let's understand the main functions of session layer. First, session interaction and session recovery. Session layer manages interaction between devices, including user logon and log off, and may include authentication protocols to verify identity. The session layer re-establish connections. That is, if a session fails or it is interrupted, the session layer re-establish connections to maintain continuity. And these functions ensure stable and secure sessions and handle recovery if issues occur. Next function is synchronization. Session layer can add checkpoints in data streams. This means it can insert markers into the data stream to indicate specific points in communication. If a communication interruption occurs, these checkpoints allow the session to resume from the last checkpoint rather than starting over from the beginning. Thereby, it improves efficiency and reliability. Next function is authentication. Session layer verifies user credentials during session initiation to ensure secure access. And next function is dialog control. Session layer manages the direction of data flow, that is determining whether communication is half duplex or full duplex. Therefore, these functions allow the session layer to support reliable, secure, and efficient communication between networked applications. And next we have presentation layer. The presentation layer transforms data into a format that the application layer can accept for transmission across the network. For example, from ABCD coded text file to ASCII coded file. The presentation layer is sometimes called a syntax layer because it converts the data and graphics into a format that the application layer can display. The presentation layer is key part of software design, especially in layered architectures like 3-tier model. The 3-tier architecture includes presentation layer, business layer, and data layer. That is, the presentation layer is part of an app or website you see and interact with. It includes things like buttons, text, and images. So in a common setup called 3-tier architecture, there are 3 main parts. Presentation layer. This is what you see and use. That is the user interface. Next, the business layer. This part does the thinking and processing. That is the logic of the app. Next, data layer. This part stores and retrieves information like a database. So the presentation layer is important because it makes sure the app is easy to use and looks good. Apart from that, it handles data encryption, decryption, and compression. Now let's understand the key elements of presentation layer. In software design, it focuses on creating an effective user interface and ensuring a positive user experience. In networking, it manages data formats, encoding schemes, and data types. And these are the protocols used in presentation layer. SSL, Secure Socket Layer. It encrypts data for secure communication. TLS, Transport Layer Security. It is an updated, more secure version of SSL. JPEG, Joint Photographic Export Group. It compresses and encodes images. MPEG, Moving Picture Export Groups. It compresses and encodes audio and video. So these protocols ensure data is properly formatted, secure, and ready for transmission. Now let's understand the functions of presentation layer. First, data translation. The presentation layer changes data into a format that both sender and receiver can understand. For example, converting text from ASCII to ABCD. Next, data compression. The presentation layer makes data smaller so it can be sent faster and takes up less space. For example, using JPEG format to reduce the size of image files. Next function is data encryption and decryption. The presentation layer keeps data secure by converting into an unreadable format before sending. This process is called encryption and restore to its original format when received. This process is called decryption. For example, protocols like SSL and TLS ensures a safe web connection by encrypting sensitive information like passwords. Next function is data serialization. The presentation layer transforms complex data structure like list or objects into a simple format for sending. And then it converts back into its original form when it arrives. For example, turning an object into JSON string. So these functions ensure data is compatible, secure, and efficiently transmitted across systems. And finally, we have application layer. The application layer is top OSI layer, which is closest to user. This layer provides network services directly to user applications. It acts as an interface between user and the network. It enables applications to initiate communication with network and send data to the presentation layer for further processing. The application layer does not include the actual software applications that user interact with. That is like web browsers, email clients, or file transfer programs. Instead, it serves as a framework that supports these applications. This layer provides the necessary protocols such as HTTP, FTP, DNS, and SMTP, which enable these software applications to communicate over a network. These protocols define the rules and conventions for data exchange and ensure that application can send and receive information effectively. Here are the key elements of application layer. First, network services. Services like web browsing, email, and file sharing are implemented at application layer. Protocols such as HTTP, SMTP, and FTP operate at this layer to provide these functionalities. Next, data exchange. Application layer handles the formatting, transmission, and reception of data between applications. It ensures the data is properly packed and understood by both sending and receiving applications. Next, API integration. APIs are often designed to operate at application layer, which allow different applications to communicate and share data. Next, user interaction. The application layer provides the necessary interfaces for user interaction, which allow user to engage with applications through graphical user interface or command line interface. This layer ensures that user requests are processed and that responses are delivered back to the user. These are the protocols involved in application layer. HTTP, Hypertext Transfer Protocol. It is used for transferring web pages. FTP, File Transfer Protocol. It is used for transferring files between computers. SMTP, Simple Mail Transfer Protocol. It is used for sending emails. DNS, Domain Name System. It translates domain names into IP addresses so computers can communicate. Now let's understand the functions of application layer. First, file transfer. The application layer helps in sending files from one device to another. It prepares the files for transfer and uses protocols like FTP to manage the process. Next, communication and authentication. It ensures that receiving device can accept the data and the necessary communication tools are available. It also verifies the identity of devices involved to ensure secure communication. Next, remote access. The application layer allows user to access services like web browsers and email from anywhere. It also enables user to manage files on remote computers. Next, directory services. It provides a shared database of information about network devices and users to support efficient resource management. Therefore, these functions ensures that application can communicate effectively and access resources without interruption. We have now covered 7 layers of OSI model and their functions. Now let's see the key differences between OSI model and TCP/IP model. In next video, I'll explain the TCP/IP model in detail. Even though the OSI model is a popular framework for understanding networking, there are several alternatives, which are TCP/IP model, hybrid model, 5-layer model, 3-layer model, cloud reference model, and simplified OSI model. TCP/IP model is a practical framework which consists of 4 layers, and that includes application layer, transport layer, internet layer, and network interface layer. It serves as the foundation of modern internet and widely used in real-world networking applications. And next, hybrid models. These models combine elements from both OSI and TCP/IP model. It offers greater flexibility and adaptability. An example is DoD model, which is used in military context and simplifies networking concepts for specific applications. And next, 5-layer model. This model simplifies the OSI framework into 5 layers, which are application, transport, network, data link, and physical layer. It is commonly used in educational settings to introduce fundamental networking concepts. Next, 3-layer model. It focuses on application, transport, and network layers. It is often employed in introductory courses to provide basic understanding of networking. Next, cloud reference model. This framework describes cloud computing services and architectures, which are typically categorized into layers such as infrastructure as a service, platform as a service, and software as a service. This model is useful for understanding the nuances of cloud technologies. Next, simplified OSI model. This model groups OSI layers into broader categories for easy understanding. The OSI model is great for learning, but alternatives like TCP/IP model are more practical for real-world networking. Each model has its use based on context and purpose. Now let's understand the TCP/IP model in a simpler way. This model is the foundation of Internet. It has just 4 layers, which are application layer, transport layer, internet layer, and network interface layer. Application layer handles user interaction and application services. For example, HTTP for web browsing and FTP for file transfers. The transport layer manages data delivery and error checking. For example, TCP for reliable communication, UDP for faster and connectionless communication. Internet layer is responsible for addressing and routing packets across networks. For example, IP for addressing and routing. Network interface layer manages the physical hardware and data transmission over the network medium. Example, Ethernet. This model is widely used in real-world networking. It is a standard model for modern networks like LAN and Internet. Now let's see a comparison between OSI model and TCP/IP model. The physical and data link layers of OSI model are combined into network access layer in TCP/IP model. This layer manages hardware connections and it is responsible for actual transmission of data over physical media. Network layer in OSI model matches the internet layer in TCP/IP model. This layer is responsible for routing data and use IP addresses to find destinations. The transport layer in both models does the same thing. It ensures data is delivered correctly between devices using protocols like TCP and UDP. The session layer, presentation layer, and application layers from OSI model are combined into application layer in TCP/IP model. This layer manages user sessions like connecting to a website. It formats data, that is, it ensures text and images display correctly. And it supports applications like web browsers and email clients. That is, this is where user applications interact with network. So this comparison shows that the TCP/IP model combines layers to make things easier, whereas the OSI model offers a more detailed and theoretical way to understand networking. Now let's understand the benefits and advantages of OSI model. Here benefits emphasize practical uses, while advantages focus on its design strengths. First, let's see the benefits. The OSI model is standard language, that is, it allows different networks to communicate easily. Next, troubleshooting. It helps to find and fix problems more easily by looking at specific layers. Next, modularity. You can update or change one layer without affecting the others. Next, it is a learning tool. It is a helpful resource for beginners to learn about how networks works. And next, scalability. It can expand and adapt as networking requirements change. Next, the advantages. The OSI model is clear structure. The organized layer makes networks easy to understand. Next, interoperability. That is, devices from different brands can work together. Next, flexibility. It works with many protocols and new tech. Next, vendor neutral. It is not limited to any specific brand or manufacturer. That's all for this session. Thank you so much.